Okay, so we'll get started with integration. So the problem that integration was originally invented to solve was I have this function f of x, so that's the blue curve here. And then I imagine that there's a region underneath my function. So it's above the x-axis between a lower limit a and an upper limit b. And I want to assign some sort of area to this region S. So often you hear integration just as referred to as the problem of finding the area under a curve. And so the concept of area, it's until there was calculus, the only way you could find the area of something was figuring out how to make it into a rectangle and then taking the area of that rectangle. And so for instance, if you had two triangles and they were both right triangles, you could sort of fit them together and make a rectangle. And then you would say, well, the area of the triangle must be half of that because there were two of them that made it up. Here it's going to be a little bit trickier because even the concept of area is a little bit less clear when you have a curved edge like this. But the approach we're going to take is just to make a lower bound for this area and an upper bound for this area. So the lower bound is going to be these red rectangles. And so I've made this diagram a little bit simpler just by making the curve upward sloping everywhere. So I'm going to evaluate the height of the rectangle at the left side of each rectangle. And that means that each rectangle is completely below the curve. And then I'm going to do just the opposite with the black rectangle. I'm going to evaluate that at the right side. So each black rectangle is completely above the curve, or the top of each black rectangle is completely above the curve. And then my lower limit for the area underneath this curve is going to be the sum of the areas of the red rectangles, and the upper limit will be the sum of the areas of the black rectangles. And I'm going to refer to this splitting up of the region AB as a partition. And what I want to do then is notice I have a little n here as a subscript for my partition. So this would be P5. It's a partition into 5 subintervals. And I can refine my partition just by breaking this up at another point. So for instance, right in the middle here, I could add another point to my partition. And then you're going to see that the red sum was going to get a little bit bigger because I could fit a little bit more red rectangle in here. And the black sum is going to get a little bit smaller because I could take a little bit away from up here. And then the idea is to look as I make my partition finer and finer and finer. So this P sub n, and I have n going to infinity. So my upper limit, my upper bound for this area is coming down as n goes to infinity. And the red rectangles, my lower bound, is going up as n goes to infinity. And so I'm going to say that if those two limits are equal, so if I let my partition become finer and finer and finer, in the limit, if my lower bound is equal to my upper bound, then I'm going to say that the definite integral of f of x from a to b, and I write it using, so this symbol here that I can't highlight, is integral from a to b of f of x dx. I'm just going to define that to be the limit of, because these are equal, I can pick either one, but I picked the lower bound, and I'm going to call that a. And then the interpretation I get after doing all of this is that a can be interpreted as the area of the region S. And then I'm also going to say that my function f of x is integrable. And this condition at the end, or this definition, means that both of these limits are equal to one another. If I were to continuously refine my partition until, and these limits, if the upper limit stayed above the lower limit, then f would not be an integrable function. So the notation or the definition of integrability is that these two limits are going to be equal to one another. And so just to get used to working with integrals, I'll go over some basic properties. So if I look at the integral from b to a, so now all I've done is I've switched the endpoints. So instead of my limit going from a to b, I'm now going to go from b to a. And let's pretend it's like the picture, so a is less than b. I'm just going to end up with minus the integral, the definite integral from a to b of f of x. And so in particular, it's sort of like area, but it's somehow a little bit different because the area of a rectangle doesn't really change. You know, if I look at it going this way or if I look at it going this way, it's the same area. But the value of an integral is going to change depending on if I'm going from left to right or right to left. If I integrate a function over an interval of width 0, so this is just a to a, the same point, the value of that integral is going to be 0. So here I let c be a real valued constant. If I look at the integral from a to b of c, that's just going to be c times b minus a. And if you imagine what this is going to look like, c says my function is constant for all x. So it's just a horizontal line. And I'm integrating, I'm trying to find the area underneath that between a and b. So if b is greater than a, b minus a is going to be positive. That's just going to give me the width of this region. And then because it has a constant height, that's just going to be a rectangle. So all I've done here is just said width times height is the area of a rectangle. And then like for the derivative, we also have a linearity property for integration. So the integral from a to b of a function that's equal to two simpler functions added together is just the integral of the first function plus the integral of the second function. Similarly, I can scale it. So if I have an integral of a function f of x times a real valued constant c, then the answer to that is just c times the value of the integral. And now I'm going to choose a point c that's strictly in between a and b. So I'm splitting up the interval ab into two pieces. And if I integrate the function f of x over the first piece and add that to the integral of f of x over the second piece, that's going to be equal to the value of the integral over the whole interval. So it's just the integral from a to c of f of x plus the integral from c to b of f of x is the same thing as the integral from a to b of f of x. And then if f of x is greater than or equal to 0 at every point in between a and b, then the integral of that function over that interval has to be greater than or equal to 0. And also, if f of x is greater than or equal to g of x at every point in the interval, then the integral of f of x over the interval is greater than the integral of g of x over that same interval. Oops. And then this number 9 is essentially the same thing I did with my partition, except now I just have a partition of size 1. All I'm saying is that if f of x is greater than some constant m over the entire interval and less than some constant capital M over that interval, then I can make a lower bound and an upper bound for the integral by just saying that this integral, this rectangle that fits entirely underneath the curve, that's going to have an area smaller than the value of the integral. And this rectangle, where the curve fits entirely inside the rectangle, is going to have a value larger than the value of the integral. Okay. And so just a quick example of how we can use this area principle to evaluate an integral. Suppose I want to evaluate the integral from 0 to 4 of 4x minus x squared. So it's not really clear how you could do that right from the start. But I think if I change this function around a little bit, most of you will recognize it. And if you don't, I'll tell you what it is at the end so it makes sense, hopefully. So the first thing I'm going to do is just write it backwards. I want to have the x squared first. So I'll say minus x squared minus 4x. And then I'm going to add and subtract 4. So really what I'm going to do is underneath the square root, I'm going to add 0 to this quantity. But I'm going to pick a very special value of 0 that I can write as 4 minus 4. And so I'm going to put the positive 4 here. And then because everything in the quantity is going to be negative, if I put the positive 4 here, that's my 4 minus 4. But now we can recognize this as x minus 2 squared. So I can rewrite, oops, what have I done? Maybe I have to keep hitting that. So now I can recognize this as x minus 2 squared, the integral from 0 to 4. And I think I have my picture here. So this is what this function looks like. And in fact, if you get rid of the square root here, if you think of this function as y equals f of x, then what you're going to have is y squared plus x minus 2 squared equals 2 squared, which is just the area of, or the equation for a circle with center at 2, 0. And so that means that I can use my area interpretation, because I know how to compute the area of half a circle, to say that the value of this integral is equal to 2 pi. And just in case you forgot, at the bottom there, I wrote the equation of a circle with center at x naught, y naught.